Yes, I guess.
Okay, hello everybody. I see it's on the hour at where I am. So yeah, let's get started. So welcome everybody to the second installment of the joint WCRP WWRP webinar series on monsoons. So the first one was held on the 13th of September and it focused on the global monsoon system. You can find the video online, but please don't go check it out now and stay along for today's webinar. And today we'll be zooming in a little and focusing on the Asian Australian monsoon region. A quick round of introductions. So hello, my name is Thea Turkington. I'm from the Center for Climate Research Singapore and a member of both the CLIVAR GEWEX-Monsoon panel as well as the Regional Working Group on Asian Australian Monsoon. And I'm pleased to be co-chairing this webinar today. Our other co-chair is Dr. Gill Martin from the Met Office Hadley Center, and she is also a member of the Monsoon panel and is actually the co-chair of the Regional Working Group on Asian Australian Monsoons. I'll be saying Asian Australian Monsoons a lot today, I think. And we also have with us two excellent speakers, Professor Goswami from Cotton University, India, and Dr. Tim Cowan from the University of Southern Queensland, Australia, and the Bureau of Meteorology. But I'll give full introductions for these gentlemen later. So just a bit about how we'll go today. So Joe will first give an overview of the Regional Working Group for Asian Australian Monsoons, and then we'll move to our two speakers who will give their presentations. So after this time, we'll open up the Q&A session using the Q&A box. We will not be monitoring the chat for questions, but we do encourage you to enter all your questions as we go along into the Q&A box so we can have a lively discussion at the end. And just noted, everybody, we will be recording. I think we're already recording this webinar and it will be available at the end. Okay, so I think that's about it. And I would like to hand over to Jill to say a little bit more on the Asian Australian Monsoon Working Group. Over to you.
Okay, thank you very much, Thea. And I would like to add my welcome also as co-chair of the working group to everybody to this webinar. So the Regional Working Group for the Asian Australian Monsoon sits under the Monsoons panel, as Thea mentioned. And as you can see in the picture, the Asian Australian Monsoon covers a large part of the world. It covers approximately a third of the global tropics and subtropics, and it affects about 3 billion people. We have 4 areas of regional monsoon, but obviously some subregions within that. So the East Asian Monsoon, the South Asian Monsoon, the West and North Pacific, and the Indonesian Australian monsoon. And all of these regions have both summer and winter because we're covering both hemispheres with the monsoons. And generally we have in their summer seasons, the enhanced precipitation generally favoured over South Asia, East Asia and continental Southeast Asia during the boreal summer, and over Northern Australia during the austral summer. Oops. So the Regional Working Group, in order to try and represent all of these many different regions, we have 17 scientists from the international community. We have representatives from countries throughout the Asian Australian monsoon region. So from Australia, China, India, Indonesia, Japan, Nepal, the Philippines, Singapore and Sri Lanka, as well as myself from the UK and Animal Life from the USA. And we have also a range of different disciplines. We thought this was important in gathering the members for the working group to include a range from underpinning research through operational forecasting and observations, because all of those aspects are clearly important to understanding and predicting the monsoons. So there is a set of our mugshots for the panel, nice range of different disciplines and also of different career stages. So we have some early career scientists as well as more established scientists. So our overarching aims as a working group, what we want to do is to try and promote and facilitate active engagement and interaction among researchers, the operational forecasters and the stakeholders for the different regional monsoon components of this large monsoon system. And we want to try as a working group to provide some authoritative information on process understanding, on the model skill and fidelity in their representations of these different regional components, and also of the overall prediction skill on different timescales. And in order to do that, we've organised ourselves into 3 subgroups. So we have a group that focuses on monsoon processes and teleconnections, one that's more focusing on research to operations, particularly focusing on Southeast Asia, and one looking more at high impact weather events. And these groups are at the moment employed in lots of activities. So the Monsoon Processes and Teleconnections group is looking generally at monsoon processes and teleconnections in observations, but also then comparing with models and focusing on prediction skill. And also that group, along with the working group as a whole, is interested in looking at the recent monsoon seasons, comparing one year with the next, and also looking at how the wider scale monsoon processes and teleconnections are affecting what's seen on the regional scale. The R2O group has been developing a regional monsoon index for Southeast Asia, which is a complicated area as it sits across the equator. So it doesn't necessarily see these very distinct monsoon seasons from summer to winter across the year. And you get very different effects in some of the different regions. So that's been a difficult thing to do, but they've been formulating a Southeast Asian monsoon progression index using reanalyses, and they're using reanalyses and testing that. And they actively take part in one of the Climate Outlook Forum groups for the Association of Southeast Asian Nations, and discuss there with the stakeholders and the forecasters how good this index might be for monitoring of the monsoons in the different regions of Southeast Asia. And then the third subgroup, which is looking at high impact weather events, is looking at case studies from recent years to look at how well they were forecast, how well they were observed, and whether the forecasts actually affected the decision making. And the idea of that group is to kind of consider and document what makes a useful weather warning, because a good prediction isn't much good if it's not communicated well or taken up by the people affected. And similarly, a poor forecast may still have some useful aspects depending on the timescales and the regions involved. So those are our three subgroups. We also get involved in some other activities. So there are, as I mentioned, these regional climate outlook forums for different parts of the region. They bring together the national, regional and international researchers and forecasters to produce the climate outlooks based on the model predictions. And that allows, our participation in that allows the group to try and provide some guidance on model strengths and weaknesses, and also to engage directly with stakeholders. So several of the group members participate in several of those on a regular basis. We also try to engage with the research community by joining international conferences and workshops, either to present or to convene sessions, and particularly encouraging research in this field among early career scientists. Because it's always great to have new ideas, fresh ideas coming in to this wide area of interest. And we do, as I mentioned before, with the subgroup, the first subgroup, aim to look at the characteristics of the monsoons as we go through the years. Having the group meeting regularly means that we can monitor what's happening in the different countries and of our regional monsoon, and look at, for instance, unusual features, extreme weather events. And we want to try and document some of those characteristics in order to motivate research and collaboration among the monsoon community. So that's a brief overview of what we do as a group. Hopefully that gives you an idea of what we're about. And so it's probably time then to move on to today's speakers. So I'm very delighted that we've got two such eminent speakers to talk across actually some different aspects of the monsoon. So different scales and different focuses. So I will hand back to Thea to introduce our eminent speakers.
Thanks, Jill. Yes, and thanks for your presentation and introducing our working group. That's great. Yes, and if you do have any questions, please feel free to pop them in the Q&A box. So yes, so as Jill said, we're moving on to our two speakers. And also, as she mentioned, that one of the aims of this working group is to promote and facilitate exchange between different communities, the researchers, operations, stakeholders, in different regional components of the Asian-Australian monsoon. So our two speakers will be speaking from different perspectives, more research and then more operations, as well as different locations as well. And we've also asked our presenters to include a slide at the end on what, in their opinion, is one of the key outstanding challenges or gaps in either predicting or projecting monsoons in our region. Okay, I would first like to welcome Professor B.N. Goswami. So perhaps, Jill, you can stop sharing, and Professor Goswami can start his sharing of his screen. And while he's doing that, I can give the proper introduction. So
Yes,
Professor Goswami. Sure, you're good, great. Professor Goswami is a climate scientist specializing in variability and predictability of the climate, and with a focus on the Indian summer monsoon and particularly the role of ocean-atmospheric interactions. He is very well known, particularly for his discovery of the Indian Ocean dipole mold and also quantifying the increasing trend of extreme rainfall events over the Indian region. So not only does he have more than 200 peer-reviewed publications, while he was leading the Indian Institute for Tropical Meteorology in Pune, he transformed it into a leading center of excellence in climate science. So with this extensive and impressive background, Professor Goswami will give the first science talk focusing on the impact of climate change on the Indian monsoon. So I see your slides are up there. So Professor Goswami, the floor is yours.
Thank you so much, Thea. And thanks everybody for giving me the opportunity to talk to you in this forum. So today, basically, I'll talk about Indian monsoon and impact of climate change on Indian monsoon. Over the last few decades, I have noticed that we are focusing more on global monsoon and less on regional monsoons. But I think global monsoon is more esoteric in terms of applications, but regional monsoon affects lives and livelihoods. And therefore, we need to focus more on regional monsoons and understand some of the areas that we still don't understand about the regional monsoons. My focus will be to talk about what we know about the impact of climate change on Indian monsoon and what we don't know about it. But at the same time, I will also focus not only on climate change impact, but a little bit about what are the gap areas of understanding the regional monsoon, like the Indian monsoon in particular. And of course, in terms of climate change, one of the areas of uncertainty or the gap area is the uncertainty in the projection of the Indian monsoon by the models. And the models have very large biases in simulating the Indian summer monsoon rainfall distribution and their intensity, and that leads to large biases in the projections. So how do we minimize them? How do we improve them? This is one of the major challenges that we are facing. So I'll just talk a little bit about that, but most of it, let me first talk about what are the key areas that the Indian climate change probably affect the Indian monsoon. I believe that there are three really different key areas that are affected, or key aspects of Indian monsoon that is affected by the climate change. One of them is, of course, the extreme events. The frequency and intensity of the extreme events are increasing, and over the last, we have several years ago, we saw this in this study. We saw that the frequency and this is the frequency of the some of the extreme events greater than 10 centimeters per day, as well as the intensity of those events are increasing rapidly. And at the same time, the number of small and medium events are decreasing. This is the number. This is collected over the whole central Indian region. So this is not individual extreme event, but this is kind of the climate aspect of the extreme events. So this is somewhat easier to understand because with the global warming, the moisture content in the atmosphere is increasing, and it is making the atmosphere a little more unstable. As a result, the instability with a small perturbation, the instability grows bigger and faster, and that makes a bigger event. And when it produces a big event, it also drains out a lot moisture, drains out energy, moisture from a larger region, and produces that rain, that extreme event. and thereby requires a longer time to bring to equilibrium under unstable condition again. And within that period, the number of smaller and events decrease. As a result, number of smaller and medium range events decrease. So this has been known, and but something is yeah. So we also found that the intensity of these I'm sorry, the last one. This particular thing is not intensity. This is the more very severe events, 15 centimeter and more. Those have actually doubled within this 50 years period. Now, we also find that the intensity of these, the heaviest events that occur during a season, for example, we took about 4 of these heaviest events, the average of that event, that intensity has also increased, and that has increased quite significantly. For example, 40% increase in the last 50 years. So this is bigger. So these are something that we knew we knew quite some time back, but but at that time, the data that we had were not, the daily data that we had were not very long. But when the longer data were available, people looked at the extreme events over a longer period of time from 1901 to 2014. And we see that the same increasing trend is there, but it is modulated by some multi-decadal variability. So, so with this longer data, we are able to actually create sort of see a kind of climate sensitivity. How does it change? How frequency of occurrence of these events as well as your intensity? How does it scale with the global increase of global mean temperature? And we find that scales about 3 times per 1 degree increase of global mean temperature. Frequency of these extreme events, the 99.9 percentile events, are increasing at the rate of 3 times the per degree increase. And the intensity is increasing to about more than 20% per degree increase of global mean temperature. That's quite large compared to the glacial scale pattern, what we expect about 7%. So this is essentially due to the associated dynamics in this region. The monsoon has a large scale updraft, and therefore these helps this increase the intensity and the stronger for stronger events to happen. So interesting thing is that this increase is not non-linear, and it is happening mostly in the recent 50, 60 years. And so that is a theme that we're seeing all over the, and what to estimate this properly, we have used removed the sort of extracted the non-linear trend by using empirical mode decomposition and stuff like that. So the other thing that is important is the total quantum of rainfall. The total quantum of rainfall of the seasonal rainfall is also increasing. You expect that there is more moisture in the atmosphere, therefore the seasonal rainfall also should increase, but it is not obvious because the larger scale rainfall depends on the large scale dynamics. So large scale dynamics can modulate that. Sometimes if there is a subsidence, large scale subsidence, the rainfall may not increase even though there is more moisture. So it was required that we carefully estimate what is the rate at which this seasonal mean rainfall is increasing. For that, we need a longer data. Normally, in 100 years data is not very sufficient because there are multi-decadal variability of monsoon, and therefore it turns out that if you calculate change on a shorter data, you're liable to make mistakes, and therefore the estimate will be wrong. So therefore, what we did is we tried to create as long as data possible, about 200 years of monsoon rainfall data we created by using 2 different data sets and sort of correcting their biases. And from that, we extracted the nonlinear trend and found that the monsoon rainfall actually increases at the rate of about 2.7 per degree increase of global percent per degree increase of global, about 3% per degree increase of the global mean temperature. That estimate is comparable to other estimates people have made, but I think this is much more reliable because we have used the longest data that is possible. So it is associated with, this has happened because the large scale, the vertically integrated moisture convergence is also over the region is also increasing at the same rate in the same way. And so the nonlinear trend, for example, of this large scale rainfall also is increasing more rapidly in the recent years. And so that is associated with the vertical integrated moisture content increase, which is again associated with the global mean temperature increase, but it is associated with the weakening of the monsoon circulation. The low level convergence, the wind convergence is decreasing. So even though the wind convergence is decreasing, the vertically integrated moisture convergence is increasing because of the increase in the moisture content in the atmosphere. So that is basically the reason why we are having this increasing trend. So within the monsoon region, there is, of course, within Indian monsoon, there are regions where the trend is not increasing. For example, the central India, the trend, the large-scale rainfall is increasing, but in the northeast India, which is a very heavy rainfall region, it is not increasing. In fact, it is decreasing. So over northeast India, this is the rainfall time series, which shows a decreasing trend and is also consistent with the vertically integrated moisture convergence. But that vertically integrated convergence comes from, as it happens because of the larger decrease of wind convergence. Even though the vertically integrated vertical moisture content or the available moisture content in columnar moisture content is increasing, that is the climate change impact. But this climate change is also in this region weakening the circulation much more rapidly compared to the increase of moisture content, which is eventually resulting in the weakening of the vertically integrated moisture flux content. So, and that is decreasing at the rate of about 3 degrees, again, 3% per degree increase in the global mean temperature. So it is important to note that within the regional, there is regional inhomogeneity in the increasing of the large scale rainfall within the monsoon region. And that is important. I'll come back to that point at a later time. So this happens because the large scale, essentially on a centennial scale, the climate change impact produces some sort of stationary circulations around the globe, which has a large scale ascending motion over the central Indian region, but a descending motion over the in northeast region. And as a result, we see these different trends. So, however, in this region also the trend of the extreme events are increasing. The maximum intensity of the extreme events are increasing as well as their frequencies are increasing. So, even though the mean rainfall is decreasing even in northeast, the extreme events are increasing because extreme events are local processes. It is not affected by the large scale dynamics. If the instability is strong, then it will continue to increase, and that is strong because moisture content is increasing. So, so therefore, that is interesting. And but the rate of their increase is less because now there is an inhibiting factor. So that makes that now it is not 3 times per degree, 3 times per degree increase in the global, but it is about 50%. It's large, but not large enough, as large as the central India. So and its increase in intensity is also about 12% per degree increase in this. So it is also large, but not larger, not as large as our central India. So these inhomogeneities are also important part of. So the third and the other area that where is a third aspect of monsoon where the climate change is going to and as is affecting is the distribution of rainfall. The climate, the Indian monsoon has a very unique and characteristic distribution of spatial distribution of rainfall. Wet to the west, wet to the east, and dry to the west. So this is an iconic feature of Indian monsoon. But But over the years, over the last 10,000 years, if you look at around 3,000 to 5,000 years, it was not so. The western part was quite wet in the around the Indus River. So Indus Valley civilization and the Harappan civilization and all those was happening because it was much more wetter. Now, where did the rainfall come from? How was the monsoon at that time? So is it possible that the monsoon climate change could change our monsoon to that kind of a monsoon? So this is one science question that we asked. Could maybe counterintuitive in some sense. I'll tell you why it is counterintuitive. But we asked whether could climate change actually transform the semi-arid northwest India into a humid core monsoon-like climate. Now, this is actually corollary to that question is also the question that it is conventionally thought that under global climate change, wet will get wetter and dry will get drier. But is it possible that under some conditions, the dry can get wetter? So this is a kind of question that we started with, and we looked at the sort of observation in the historical period from 1901 to the present period, and looked at the climate, the differences in the rainfall climate in the early period 30 years and the late period 30 years. That difference tells us this is the monsoon rainfall distribution, this is climatology, if you take the difference between the climatology in the early and the late periods, that indicates that this has been increased. The rainfall, mean rainfall is increasing to the west, to the about 10%, by about 10%, 10 to 25% in further to the west, and decreasing to the east at the by about 10%, and of course to the south also by about 10%. So monsoon appears to be shifting a little bit to the west, or the expanding to the west. And this appears that the global climate models can also simulate this. So we looked at the ensemble mean of the CMF6 models, and they simulate this shift quite reasonably well. Although there are biases in the models, still this seems to be a very important sort of robust signal, which even the models with all the biases were able to simulate. So when they will take the models and then ask future what would happen to in the future scenarios in the SSP 4.5 and 8.5, it looks that exactly this does get amplified. So the western part gets more intensified, increases further. The eastern part does not decrease continuously, but because more and more increased moisture, it will start increasing, but increasing at a slower rate. So there is still that asymmetry is maintained and intensified. And so by very high greenhouse gas, you expect a more 200 to 300% increase in the western part of it. So that is a huge change, and that might affect the climate of that region considerably. So that is there is an important thing that we are looking at, and that seems to come from these changes in the westward expansion of the warm pool in this region. And if we see the differences in the temperatures in the early and late period, the western part is warming faster than the eastern part, and that is what produces a westward expansion of these of the warm pool, and the westward expansion intensifies again, just like the rainfall to the western side. And that expansion essentially is essentially what it does is that it produces the ITCZ in this region is now expanded in the horizontal directions towards a little bit towards further to the west. So the westward expansion of the ITCZ when propagates, and the monsoon is essentially a propagation on this ITCZ to the north on intraseasonal time scale, and this intraseasonal propagation of the time scales also extends to the further to the west, producing wetter region in this region. So the dynamics also is clear that somehow the air-sea interaction, actually we know how I don't have time to go into great details. The air-sea interaction associated with this climate change produces westward expansion of the wormhole. The western expansion of the wormhole produces westward expansion of the ITCZ, oceanic ITCZ. This oceanic ITCZ, when they travel on transitional timescale to the land region, extends itself towards west, producing more rain in the west. And that is the basic region, basic dynamics that happens. And there is considerable amount of evidence, supporting from various associated with this. Again, we looked at more details on the data on the mean, as a mean from the IMD data. The mean also shows there is an increase in the western region and decrease in the eastern, as well as the length of the rainy season. The season is actually longer in the east and shorter in the west, and now it is getting longer in the west and also getting a little bit reduced in the east. So all these things are, and the same thing is happening in the future, and more in the future. So the distribution of rainfall is also correspondingly changing. So, and this is actually a part of a larger global change due to the climate change, and that larger change is associated with larger change of the oceanic ITCZ. The oceanic ITCZ is expanding to the west everywhere, and you can see this, that oceanic ITCZ is difference. The ITCZ is here, but this is getting intensified and expanding to the west, and becoming this is the anomaly, and it is expanding further to the west and in the west. Here also it does expand, but in the summer, because of the northward migration, and it produces more rainfall in the western land regions rather than over the ocean. So that is a part of the global phenomenon, but over because of the regional dynamics in this region, this is actually affecting the monsoon very interestingly by increasing the rainfall over the western region. So this is actually supported by model experiments where the carbon dioxide increase, and exactly the same thing is seen. Increase in rainfall here, the increase in rainfall there, and westward expansion of the rainfall. So I think it is quite robust, that it is largely related to the greenhouse gas forcing. So there is, of course, large opportunities and challenges with it. But before, since I don't have too much time, so I will quickly go to a few gap areas and what we need to do so in the future, for example. So as far as the monsoon predictability is concerned, we know that during the Toga period, we have established the basis for climate, basis for the seasonal predictability, and so has been considered as the main or the only predictable driver for ISMR for a long time. However, NCMD explains about 35% of the ISMR variability, or Indian monsoon variability. What produces the next 65%? We don't know, and nothing much has been done today. And unless we understand, so what are the new sources of predictability, I don't think we can expand, increase the scale of monsoon predictions in the future. So in this connection, we found that in a series of studies, we have shown that the North Atlantic SST actually is an additional source of monsoon predictability, and that essentially gives and there is this also shows something very interesting, something like we never thought that the extratropics can affect the tropical climate, but now we have a mechanism also how the source and mechanism, how extratropics can actually influence the tropical climate. So this is, I think, is a very important finding, which also comes from largely Indian scientists. But there is also this regional aspects. Within the region, sub-regional effects actually affect the monsoon variability on a seasonal time scale quite significantly. And in our region, the northeast is a very important heat source, and that it has a larger, significantly larger season. But traditionally, we don't consider May rainfall in the Northeast as a monsoon rainfall. But the May rainfall over Northeast is even larger than the June rainfall over Central India. Therefore, still we don't consider it. We call it a pre-monsoon. I think this has been a wrong concept because so we need a revision of this seasonal monsoon season over the Northeast. And we have shown in a series of papers again that the monsoon season over Northeast is actually from about middle of May to middle of October, and therefore it is about 5 months. And the rainfall, this additional rainfall actually has an impact on the internal variability monsoon rainfall over the country, and that is very important. So we need to therefore it affects the predictability. And so this is something very important. So I think this is something that we need to do. The other important thing is to see how can we extend this scale of seasonal predictions, because today the seasonal predictions are limited by the error growth problem on the dynamical models, and it limits our but we have shown recently that there is long-range predictability. I have made a study. It is recently published, and this study shows that Indian monsoon actually has predictably, even at 18-month lead, very high predictability. Now, how
your time's almost up. Can you 1 more minute to wrap up, please? Thank you.
Yeah, done. So lastly, so we need to find some other ways to how to accept this. How to realize this predictability. So this is something that I think. The other thing also, this reducing uncertainty, we need to work on that. We have done some more studies on that in terms of finding a emergent constraint and so on. So I think I'll stop here. Sorry for the couple of minutes of overshooting. This is a small group that I work with at Cotton. Thank you.
Thank you very much, Professor Goswami. It was very interesting. You took us through a fascinating journey from looking at observations from more than 100 years ago. You even talked about climate a few thousand years ago, all the way to the future. So it's very interesting talk. Thank you very much. I'd like to
thank you.
Thanks.
Thank you.
And I would like to remind everybody to please, if you have any questions, to please enter them into the Q&A as we go along. Discuss more at the end. So thank you very much. So if you could share.
Stops here. Yeah. Yes. Good. Okay.
Thank you very much.
Thank
you very much. Okay, and so yes, we've been focusing on India and looking at climate change long term. So now we're going to move slightly, and I'd like to introduce Dr. Kim Cowan. And while you get your slides up, I would like to give your introduction. So Tim, you can try to share your slides. Thanks. So Dr. Cowan is a senior research fellow at the University of Southern Queensland Centre for Applied Climate Sciences, and he's also part of the Seasonal Climate Processes team at the Australian Bureau of Meteorology in Melbourne. So his expertise covers climate drivers within the Indo-Pacific region and the Australian monsoon, and he's also leading the development arm of the Northern Australian Climate Program and developing very innovative prototype forecast products. So we are in Tim's very capable hands as we shift our focus from India to Australia, as well as from research to operations. So Dr. Cowan, the floor is yours.
Thank you very much, Thea, and thanks everyone for joining. As Thea mentioned, I'm based in Melbourne at the Bureau of Meteorology, but actually employed by the University of Southern Queensland. So a lot of my stuff that I do has a real applied focus to it. So through the Northern Australian Climate Program, we basically tailor forecast products for the northern cattle industry. So this is a red meat sector. So what I'll be talking about today is sort of my perspective on where our work has gone, where it's going to, and it's a real focus on, I guess, the applied side of monsoon research. So a big focus on water, on rainfall events. So what I'll be talking about today is just the importance of the Australian summer monsoon to the regional communities of Northern Australia. And when I'm talking about monsoon Australia, or the monsoon of North, I'm focusing really on the sort of above the 20 degrees south region up into the Cape York and the northern part of the Northern Territory. So I'll just briefly outline what I mean by the Australian summer monsoon, and then get into the role of the Madden-Julian oscillation, so the MJO and other tropical atmospheric waves, and then just introduce some of the forecast products that we've developed over the time, with a focus on the sort of sub-seasonal to seasonal perspective. And then lastly, I'll just talk about monsoon failures. So this idea that there's this expectation that there will always be a wet season every year, but sort of quite, it's not that uncommon that you will get a failed wet season, which can have huge impacts on agriculture and communities up north. So I like to start off really just by showing you there's some of these headlines from online media sources. So these are all from the last 2 months or so from September through to just recently. And you can see by these headlines that the media in Australia and also stakeholders that who depend on the weather and climate forecasts that the Bureau provide, they're really in tune. They're really tuned into what's going on with the weather and the climate. So these are just some headlines talking about the declaration of El Nino back in September and how it was going to lead to basically devastation throughout the cattle industry in Northern Australia. And then there's the different articles from grains through to wine. And then, of course, the Bureau were warning the northern communities of being quite a dry season because of this El Nino prediction. And at the time there were bushfires raging across Northern Australia, which is typically the end of sort of the dry season or getting into the sort of start of the wet season. And then we had this headline just came out early this week that potentially the cattle industry overreacted to that El Nino forecast, and maybe they put too many of their eggs into one basket when it comes to sort of making decisions based on purely just one climate driver. But going back to the Australian summer monsoon, it's super important for northern communities. So if you think about the north of Australia, it's actually quite it's not highly populated with people. So it's unlike the sort of east coast of Australia and the south. But we do have lots of natural resources like mining. So the cattle industry is quite big in the north. So there are about 15 million head of cattle. There's also other livestock, sheep and goats and buffalo. But also there's quite diverse biodiversity in the north as well, which are all heavily dependent on the wet season. So you got a picture of a crocodile. There's the tourism industry in the north as well is dependent on the wet season insofar as that they can plan around the start of the wet season, which is typically the quieter times for tourists heading north. But and of course, as I mentioned before, agriculture is very much dependent on the wet season. So when the wet season onset begins, when the wet season sort of tails away, and when its demise is, and of course transportation. So taking goods north and south is highly dependent on, I guess, when the onset of the monsoon starts, and also the intensity of the monsoon season, whether it cuts off roads. So what is the Australian summer monsoon? So here I'm just showing you a climatology from NCAR reanalysis. So we have November, December through to April. And essentially what you can see is that by about December, that's when the monsoon really, that's when the monsoon onset occurs. And what we sort of define as the northern part, so the northern part of the top end over the capital city of Darwin. So that tends to occur around about sort of mid to late December, so around sort of Christmas time. And we can find by the time January hits, this monsoon shear line, which is really just that, where there is that separation between the westerlies and the easterlies, that moves well over northern Australia. And then just to the north of Australia, we have that area of really deep convection. That's shown by this yellow line here. So you go through to February and we're fully embedded into the Australian summer monsoon. And then by about March or heading into maybe early April, that's when we see the retreat of this summer monsoon. And on the left here, I'm just showing you what the wind speeds are like in July and January at Darwin. So right up here in the northern central part of Australia. So typically in July, you've got these dry southeasterlies coming off the continent. And then by the time you're in the middle of the Australian summer monsoon, you've got these winds predominantly coming from the west or the northwest. In the build up to the Australian summer monsoon, typically what we see is that the continent heats up quite rapidly compared to the surrounding seas. And so you get these, what we call heat lows and heat troughs forming. These are quite shallow, so only extending around about 1 to 2 kilometers up above the surface. So typically they're quite warm. One forms over near the Pilbara region, and one forms over what we call the Gulf country of Australia. So this you can see here the heat trough over the continent, and then to the north of Australia you have the monsoon trough, and to the south you have this subtropical ridge directing sort of moist easterlies across southern Australia. And typically when you have this set up, and this is showing you what the setup was on early January of 2006, you typically get an increased thunderstorm activity, so isolated rainfall events, as shown by this rainfall map here for early January. So these are just sort of showing rainfall events around about 5 to 10 millimeters in any given day. So you're not really embedded into that monsoon period. Now moving on to sort of later January of that year in 2006, and this is again just showing what might be a typical setup for the Australian summer monsoon. These lows are now sort of deeper. The monsoon trough is shifted well over Australian latitudes, so around about 20 south. And then so those lows that deepen, you might get the odd tropical cyclone forming in the Coral Sea to the east, as shown by this event here in 2006. But what you do see are these widespread rainfall events, so these big bursts of rainfall, so typically anywhere above 25 to 50 millimeters per day. So well south of the top end area of the Northern Territory. So I went back to the literature not long ago to see, well, what is the actual definition of Australian summer monsoon? And I found a paper which actually came up with 25 different definitions of what a monsoon onset is. So I guess technically that's sort of 25 different definitions of what the Australian summer monsoon could be. The two main ones I want to just show here are the one on the left in the blue is really just defining the monsoon by the deep layer mean westerlies in the lower atmosphere. So that's from the surface through to sort of 500 hectopascals. And that's when you have easterlies above that. And when you have those westerlies conditions for about 2 consecutive days, that's when we would say, well, that's probably a monsoon onset or typically a monsoon period. On the right there is just a definition based on rainfall. And so this is for any given location. So for example, Darwin, the monsoon would be defined when the 5-day running mean of rainfall exceeds 150% of the long-term daily mean. So these are just different ways we can define what the monsoon could be. On average, if you use the wind definition, you get around 3 to 10 sort of bursts or monsoon spells per wet season. On average, they last around about 3 days in length. Whereas the rainfall definitions are slightly fewer spells per wet season, so 1 to 6 spells, but they last a little bit longer. So if we consider the monsoon as really just a series of rainfall bursts and breaks, then typically we can just show it using the outgoing long wave radiation. That's shown here in this bottom time series. This is showing you 1984 and 1985, so the months across the top here. So July through to June of 85. And this is the OLR, showing the deviations from the long-term average. And when it goes negative, so there's negative anomalies, that's what we characterize as a monsoon burst. And when you get these positive anomalies, they're considered a break in the monsoon. And they typically align quite well with the rainfall. So I'm just showing a rainfall time series here for that particular wet season. And you can see that the rainfall peaks tend to align quite nicely with those dips in the OLR. And that's for the north of Australia. So that's the top end and north into the Timor Sea. So what can cause such bursts to occur? So one of the main culprits is the Madden-Julian oscillation, and that's just shown here on the left. It's sort of like a nice little animation schematic showing what the Madden-Julian oscillation is all about. So typically, it's the main intraseasonal driver in the tropics. So it has a 30 to 60 day cycle, and you can see it's punctuated by these deep convective sort of blobs which move to the east, and then they're sort of sandwiched by these dry phases, these clear suppressed phases of the Madden-Julian oscillation. So typically they can impact tropical cyclones, monsoon depressions, and have an impact on rainfall in the summer period. And as I mentioned, they're one of the main contributors to bursts and breaks in the monsoon. But they can also impact rainfall outside of the tropics. So they can lead to these Rossby wave trains, which can then go through to the mid-latitudes and extratropics and impact other locations like North America and South America. But the MJO can also not only affect our monsoon, but it can also accelerate the development of an ENSO event through like a westerly wind burst. So it's quite an important feature for Northern Australia. So this is just a typical MJO evolution phase diagram for early this year, January to March. And you can see that the main active phases of the MJO are where it's in phases 5, 6, and 7. And typically it's in its suppressed phase in the summer, in our austral summer season. So sort of December through to March in phases 8, 1, and 2. And these are just the composite rainfall maps that are showing you what is the likelihood of getting above the average weekly rainfall, the median weekly rainfall for this austral summer period. And that's based on all MJO events from 1974 to 2021. And you can see that when you're in those active phases of the MJO, so phases 5 to 7, you get above median rainfall across pretty much the central part of Northern Australia. And as that MJO pulse moves through, the rainfall signal moves accordingly. And likewise, the suppressed phase, you get drier than average conditions over much of the north in those 3 phases. So we do a lot of customer engagement in our project, the Northern Australian Climate Program. And in fact, some of our local extension officers are really keen to know more about the Madden-Julian oscillation, because they know a lot about ENSO or the IOD, and they ask really good questions like, you know, oh, the MJO has been strange, or it's been quite weak for a couple of maybe a couple of cycles. What's going on? Or they want to know, well, what is the impact for my particular region? So it shows that our customers are really engaged with the weather and climate knowledge, and they want to know. Obviously, they care about what the impacts are of these, like say, heavy rainfall events or dry periods, but they want to know, well, what is causing those conditions. And actually, our project in helping out the northern cattle industry, that was the main sort of impetus to actually update the monitoring of the MJO at the Bureau of Meteorology. So the maps that I'm showing you here, so rainfall, temperature composite maps, OLR, and geopotential height at 500 hectopascals. Those updated maps were actually at the request of the northern beef community. So you can see the impact that our stakeholders have on developing products and also helping with the monitoring of climate drivers. But it's not just the MJO that we're interested in. We're also interested in other tropical atmospheric waves. So the Bureau do offer a forecast service or a forecast product of not only the MJO shown up the top here, but also Kelvin waves, which actually travel slightly faster than the MJO, but they're about 12 to 25 meters per second, but also the equatorial rossby waves as shown on the bottom here. So this is just a mix, as you see the animation go through, a mix of observational analysis and a forecast. And so you can see that any user can sort of see what the rainfall forecasters look like, and then go to these forecast maps and these animations and see, well, what is going on in the atmospheric waves? Can we make sense of what's happening? And in fact, I'll give you an example of this, why atmospheric waves matter for understanding a particular rainfall or temperature forecast. So this was this is the MJO phase diagram from January to March, as I showed before. And I'm focusing on the 23rd and 24th of February. So sort of late February, when the MJO was in that inner circle. So it was quite weak. And so on the top right here is the MJO forecast in terms of the OLR. And you can see that there was a sort of a convective signal north of Australia, but not sort of encompassing much of sort of the northwest. But if we see what the actual rainfall totals were like in that late February period, we can see rainfall stretched right down the northwest coastline. So this is sort of the Kimberley region, even getting into the sort of the Pilbara and so into sort of the desert areas of Northern Australia. And the reason this happened was because there was an equatorial rossby wave that actually passed through and actually extended as far south as the northwest of Australia, so this Kimberley region. And it was able to generate weather systems which led to rainfall totals of 25 to 50 millimeters on one day. So other forecast products that we have developed as part of sort of the monsoon, our monsoon work for the Northern Australian Climate Program. So the Northern Rainfall Onset is one such product. So this is actually sort of a proxy for an onset, but it's not the monsoon onset. It's more a proxy for pasture growth. So after the dry season in the north, it's defined as when you get 50 millimeters of rainfall after the 1st of September. So 50 millimeters total. And showing you on the left here is just an animation of the daily forecasts of whether this northern rainfall onset was going to be early or late for 2023. And you can see the brown colors indicate that it was going to be like our forecast model was suggesting it was going to be later than normal. And on the right here, I'm just showing you that we do an ongoing monitoring of what the northern rainfall onset has or is from the 1st of September. And this is our current maps of what's been happening. And you can see this is just the total, sorry, this is just the date of when the northern rainfall onset has occurred for this current season. And then the bottom map is showing you whether it's earlier or later than usual. So in some ways, it's a way of sort of verifying the forecast. You can see that where there's blue, that's indicating that the northern rainfall onset actually occurred earlier. And so you can see that the forecast for those regions was probably not that great. Another product that we've developed as part of our program is this 3-day rainfall burst product. So it's essentially, it looks at what the likelihood of a 3-day event rainfall where you go above a particular threshold. So it might be 15 millimeters, might be 25, or it might be 75 millimeters. So it's up to the customer to decide what threshold they want. And then they end up getting a map like this, which gives them a probability based on our sub-seasonal to seasonal forecast model. So it was actually developed for the northern beef industry, but it is now an operational product at the Bureau, and it's used across the country. And it's really good during the Australian monsoon season, to give producers a bit of an idea of what's the likelihood of there being a significant rainfall event in the next 1 week or next two weeks. Other products also include tropical cyclone forecasts, which is a new thing that the Bureau offer now, and we also give seasonal sort of forecasts of the outlook for the number of tropical cyclones. So all sort of relevant to the summer monsoon. And we also provide a service not only for Northern Australian communities, but also for the Pacific in general. So this is just showing a rainfall probability map of terciles for the Southwest Pacific. And we provide this sort of service, and we can also link it in with the MJO forecasts for those communities to get a sense of, well, what is the sort of seasonal outlook ahead. So it might be the next 1 month or next 3 months. And finally, just getting onto the failed wet season. So this is where I come back to my point about expectations versus outcome. So back in February and April, between February and April of last year, the Northern Territory had a bit of a failed wet season. So that's shown by these red colours here, showing you very much below or even lowest on record rainfall for that 3-month period. So typically, where you see those large reddish colours, that region would normally see around 150 to 300 millimeters of rainfall, but during those 3 months they only got less than 50 millimeters. So it's quite devastating for the communities that live there and depend on that rainfall. And the forecast that the Bureau put forward back in January was for the east to be quite wet, so the sort of northeast Queensland and down the east coast. But for the Northern Territory, it was indicating that there was probably a 50-50 chance of it being median rainfall for that time of year. But what we didn't anticipate was that there was going to be a volcanic eruption. So that the Hunga Haipai volcano, which erupted on the 15th of January, so 5 days after this forecast was generated. And that led to a significant water vapor explosion into the stratosphere. And this circled the globe, I think was around about every 18 days or so. And we believe, and this is ongoing research, this is where research and sort of operations can mix quite nicely. We think that it impacted the MJO signal coming through, and we should also say that this was a La Nina season as well, so we would have expected it to be probably at least average to above average rainfall for that time of year.
Okay, sorry, Tim, if you could wrap up 1 more minute.
Thanks. No worries. And so we believe that it led to a failed wet season because it disrupted the MJO's convective sort of reach to Northern Australia. But this is ongoing research that my team at the Bureau are currently working on. So this is my last slide, so it's good timing. So what are some of the challenges that we have going forward? So I think for Northern Australia, it's really this idea that there's actually quite poor skill in predicting summer rainfall, and trying to understand how we can improve that skill going forward. I think that would be that's actually a fairly big gap, and that sort of leads into the MJO skill as well. So we have pretty good skill at predicting the MJO out to about sort of 20 to 30 days. However, we have issues with our current Bureau seasonal model in actually depicting the convective reach of the MJO, so the impact of the MJO on convection over parts of Northern Australia. So that's an area I think where we probably could develop moving forward. And the last thing I think is a challenge is just the messaging to our customers or our stakeholders. So this idea that a forecast has a certain amount of skill, but of course, when you have a forecast for a given season, there are sort of sub-seasonal processes that we don't have great skill beyond, say, a month, which could sort of disrupt that sort of maybe long-term climate signal. So I'm just showing you this example here where you have that headline which I showed before about cattle prices crashing because of El Nino. And this is just a headline from, I picked it up today actually, and it talks about the heavy rainfall that's just occurred over parts of the East Coast and up into northern Queensland, and that's led to cattle prices going up back to levels that they expect. So yeah, so it's all about our customers, and I'll leave it there. Thanks, Thea.
Thanks very much, Tim. That was really great. You, in some ways, a lot of your messages actually overlapped with the previous talk, but you gave a completely different view, focusing on having to take that science and actually get people to use it, right? That's what we do science, right? Is so that we can go and help people save lives, save money, and whatever.
Absolutely.
So yeah, thanks very much, Tim. So yes, we are now into the Q&A section. And before we start, I would like to remind everyone to please enter your questions into the Q&A box. That would be great. And so, yes, I think everybody has their camera, or maybe I could ask also Professor Goswami to turn your camera back on so we can welcome you all, our previous speakers, as well as Jill, onto our virtual stage. Thank you.
Sure.
Yeah, thanks.
Okay.
And before we get to the questions in the chat, I want to give some time for people to also ask questions for Tim's presentation as well before we go on this. I have one actually for all three of you. I think the thing that struck me from both the presentations, and to a certain extent also Jill mentioned that as well, there's a lot of the monsoon everywhere, but we're focusing on Asia, Australia, is very complex, right? But we're trying to do this in science, in communication, and whatever, to simplify it to be like, here's when the monsoon starts. This is when the monsoon ends. This is our wet area. This is our dry area. And I'm wondering, like, from your opinion, from research and in developing products, should we be trying to do this simplification, or should we be trying to be more open and honest about, hey, it's complex what we're doing, right? Like, is this only just starting right now? Okay, I don't know. Is this the start of the wet season? I mean, it's all very variable. It depends on the data set, the definition, all this. So yeah, should we be in our approach, I guess, more for Professor Goswami from the research, but maybe Tim more from the operations, should we be trying to embrace in our results and our messaging that is everything complex, or should we be keeping on that we are trying to simplify things to make it easier to understand? Catchy headlines.
Okay.
Yeah, so who would like to take this first?
Sure, you want me to go? Okay.
Sure.
So in terms of, I think, the science and we know that it is complex. As I mentioned in my last slide, the complexity is what is actually making it difficult for us to extend our scale of predictability, because that is what complexity is nothing but event-to-event variability in terms of event, or in terms of spatial variability. One space is different from another place. So the space variability and event-to-event variability and that is not periodic, and that is complex. That is complex because however, that small scale variability has an impact on the large scale, and the large scale has an impact on this. These two cannot live without each other. They depend on each other. But because of that, the large scale, the predictability of the large scale also gets affected, and there is a limit on predicting the small scale. When it comes to smaller and smaller scales, we know that the predictability is shorter. So in terms of communication, it is important that we communicate that something we are not able to do, because there is certain intrinsic limit. For example, in India, we see that we want to go for very high resolution prediction of very small scale rainfall process in the block level, very small scale, 10 kilometer, 20 kilometer time scales, spatial scale. But I think it is almost impossible to do that in a deterministic way. So we have to go to communicate it properly, that there is a limit. And the policies and advisories must also be framed with that in mind. That these are a certain limit, but this may be the probability. But today I think even though we cannot deterministically predict or give a but we know a little better about probability, because now we can do a lot of experiments. We have better resolution models and so on and so forth. So and ensemble members and so on. So we can make a much better probability. So the probability is important. A lot of decisions have to be made on probability, but we have to communicate that correctly. I think that is what I feel is, in terms of sense of your question, in terms of science, it is there that is we cannot deterministically say something about very small scale or very short time scale phenomenon. And there are limit to that. Even on a seasonal time scale, there are limit to predictability. But we must say that, okay, I can do only this much, and there is certain amount of uncertainty on this level of forecast. So I think that communication, I think the people like Tim and others who are actually applying it to the user, we need to translate that appropriately.
Thank you very much. Yeah, I agree. Focusing on probabilities. Thank you very much for the answer. And so, Tim, do you have something to add to this from your perspective?
Yeah, look. So in my role at the university, I do a fair bit of extension work when I get a chance, because I'm based in the south and a lot of our work is the north. And so we go out and we actually talk to graziers, cattle farmers or beef producers, as we call them in the north. And there is a real appetite to understand even quite complex, some of the complexities of the science. So when I first started, I thought, oh, there's no way a grazier is going to understand the MJO, let alone convectively coupled waves. But it's actually, we've found through the lifetime of the program, which is now we're sort of 5 years into the program, that there is a real appetite, and graziers want to know what is driving my weather, what is driving the climate, and I think they want to move beyond the whole, it's all just ENSO or ENSO and the IOD, so that they want an understanding of, well, what is the MJO? And I showed one of my slides, which I didn't actually talk about it, but one of our colleagues in the program, who's a beef producer in sort of southern Queensland, she uses this idea of explaining the MJO as sort of like when it's sort of quite active, so above the unit circle. She says, oh, it's like a sheepdog chasing a cow or chasing a bull. But when it's in the inner circle, it's the dog's in its kennel, and it's too shy, or doesn't want to leave its kennel. And I think using that sort of analogies and different ways to explain sort of complex ideas is useful. And I think in most of the correspondence that we've had, is people really appreciate it. So yeah, I think there are ways to sort of communicate complex ideas, and at least in my experience, customers, they do appreciate it.
Thanks. I think you sort of answered one of the questions already in the Q&A box that was for you, that really is it, how useful is it for forecasters and end users, the MJO, because that is of course good diagnostics for understanding processes and model development. So I guess your answer was it is useful for at least the grazers and I suppose workers as well. Thanks. Great. But before I go into more questions, Jill, do you have anything to add to this? Are you?
I was only going to concur with both. I think, it is complicated, and I don't think we should hide the fact that it's complicated and that we can't predict everything. But I also agree with Tim that, we need to try and communicate what we can do and what we can't do, and try and communicate it clearly, and don't shy away from trying to help people understand how it works. Somebody asked, I think, in one of the questions about why haven't we made the models better? And the reason we haven't made the models better is because it's complicated. And there's a danger of people saying, well, you're wasting your time. You're never making anything better. Let's not bother. But we do need people new to come into the field. We need to keep working on the understanding of this really complicated processes that come together in this emergent phenomenon that is the monsoon. And so I think we need all of those aspects of the research to come together, the underpinning, to really understand the processes, the model development, the parameterization development, and then through to the predictions, understanding the skill, and then the communication side. And I think Tim's point about expectation versus outcomes, managing expectations, but also doing that in a kind of scientific way of saying, this is how things work, and therefore that's why, you can expect this. and possibly not that. So yeah.
Thanks very much. So I'll turn to the Q&A to ask for my next question, and I see one has a couple thumbs up, so I will ask this one first. So this is to Professor Goswami. Thank you for the great talk. And it seems that from various papers that extreme precipitation, these are like fine space and time scale localized events, are increasing. I think you also showed increasing extremes in your presentation. And it's also known that the seasonal forecast scale is driven by large-scale, slowly varying boundary forcing, such as SSTs, right, and things like that. And the scale of high-frequency synoptic variance in seasonal scale is insignificant. So how do you feel the scale of these synoptic transient features can be improved in the seasonal forecast? Can it be? And is there a source of predictability that can be used to achieve this?
Oh, that's a bit long question.
So I guess I can try to rephrase it shortly. Is how can we? Oh, you understand? You understand?
I think I understand generally. So I think I do understand that the high frequency has an important role in the seasonal predictability, because we know now that that MGO or even MGO has a contribution to the seasonal mean. Similarly, our monsoon intraseasonal oscillations have a contribution to the seasonal mean, and in addition to that, the synoptic disturbances also has a contribution to the seasonal mean. So, in any model, if they are not resolved properly, we cannot expect the seasonal mean to be realistic. So therefore, they must be realistically simulated. All these components must be realistically simulated in a model so that the seasonal mean is simulated. So in fact, there is a strong relationship between the resolution that and the seasonal mean, because if the resolution is very poor, then you don't expect the synoptic disturbances and the as the extreme events to be simulated correctly, and therefore it will have an impact on the seasonal mean. Seasonal mean will be weaker in terms of rainfall, at least in the monsoon. So it is very clear. So the point is that in terms of predictability, it is difficult to say, because the seasonal mean, the intraseasonal and the synoptic events has a residual which comes into the seasonal mean, which can be stochastic, because we don't know how that contribution affects the seasonal mean. So therefore, seasonal mean is affected. We are beginning to understand some way how the intraseasonal is affecting the monsoon, but and same thing that synoptic disturbances. But what is the sort of spectrum of that in kinds of how periodic they are? They are not periodic. So how do you, what kind of internal variability they introduce in the seasonal mean is not very clearly known, and that is essentially limits to a certain extent. Although we need them to be simulated correctly, which in turn will add some internal variability in the system, which will limit. But the mean itself is very important, because if they are not there in the proper strength, the mean will be underestimated, and therefore that will affect the predictability. So it is a sort of difficult problem, but I think ideally we need a very high resolution model to simulate all this correctly, and see how we can control the growth of errors in those models. I think that is the only way I can think about. But it is essential that we have to go into high resolution models which can resolve these and simulate their statistics at least correctly.
Thanks very much for that answer. It's a very tricky situation, right? So I have another one on this, like improving of the models. So there's another question, the one after it, and it's about just process-based verification. Can this help solve the identification of sources of systematic errors in rainfall, or I guess any fields, in operational models? So I'll ask this to both of our speakers, like maybe start again with Professor Goswami, and then also ask him as well. So yes, if we use this process-based,
maybe Gill can
or Gill as well.
Yeah. I think she will be better equipped to answer this question.
Sure, Jill.
So I think it contributes. I mean, I think we have been, I think people working in model development and monsoon underpinning research have been trying to do this for a long time. So I think we definitely should be concentrating on the processes and trying to verify the processes. I mean, I was thinking back to your point a moment ago, Professor Goswami, about resolution, and I agree that resolution is important, but it isn't. There's no evidence that it's solving our problems just in its own right. So we do need the process representation to be improved as well. We need the parameterization development. And in order to improve our parameterizations, we do need to be doing the process-based verification against observations as well. So I think we need both of those. So I think it can definitely help in identifying the sources of systematic errors. One of the other problems that I've found over doing this for a long time now is that finding where the source is not the same as solving it, because we don't necessarily have very good ideas yet, or good enough ideas about how to improve the parameterizations in the right way. And one of the problems, of course, is also that we have to have these parameterizations and models working for the whole globe, not just the monsoon. And so we certainly find in our model development that we can make the processes better, but they don't necessarily improve the monsoon. They might improve other parts of the globe. And so it is complicated, but I think there's definitely that's definitely one of the routes that we need to be pursuing, is looking at the processes and verifying against the observations. One of the other questions that's asked is about the lack of observations or detailed observations, and that's clearly something that comes up a lot over land and particularly over the ocean. So that's another important aspect, is getting the right quality and quantity and frequency of observations in order to do this well.
Thanks, but yes, I think identifying a problem hopefully is like the first step towards solving it. If you don't know it's a problem, so even if you can't solve it yet, it can be good to identify it. Thanks very much. Tim, do you have anything you'd like to add to this as well from an Australian perspective?
Yeah, so we have someone who works in the UK Met Office, so Sally Lavender. She might be in the audience, and she works on the parameterizations or on improving the convective part of our models through comorph. And we have done things like at the Bureau look at particular case study events where we pull apart a single event, and it's usually I'll give you an example. So the 2019 floods in the northern part of Australia, in the Gulf and in Queensland, which was devastating for the cattle industry there. We did look at that one event and looked at the forecast, the predictability of that event, and then we pulled apart some of the processes that possibly were reasons why it wasn't so well forecast. So issues to do with sea breezes, even just initializing the model. So yeah, we in our program, even though it's quite applied, we do have a research component that does focus on trying to improve the basic sort of physics of the models, and then down the track that will eventually feed into improvements in our seasonal forecast model at the Bureau.
Great. Thanks for sharing. On this topic of improving, so we heard about this process base. We also heard, as Jill mentioned, there was an earlier question about observations. Maybe we can come back to that. And again, how do we overcome this issue with observations? But there was also a question which Professor Goswami did answer in the chat, but there was around the role of AI machine learning. There's obviously, the question was saying that there's limitations especially with the extreme events, but maybe to ask the question, does this see something that can perhaps improve our understanding, prediction or projection of monsoons in this larger region? Okay. Anyone like to take that on? That question?
You want me to answer?
Sure, please go ahead.
I mean, I have some idea, but it's kind of early days. But I think what is as I was trying to towards the end of my talk, I was trying to say that I think we have a limit on predictability by dynamical models because of the because of the error growth problem. No matter what, the dynamical models may never be able to predict seasonal mean beyond a certain. I think, for example, today the seasonal mean prediction is basically on monsoon. Most models can predict only 1 or 3 months in advance with some skill, but more than in 6 months in advance in any skill is very difficult. And so, of course, has a longer skill, and so prediction. But even then, there is a skill goes down with increasing lead. So this happens because of the error growth problem. Now, I think this is where the AI can probably help us, because they are probably, if we can understand, basically any lead time forecast depends on the relationship between your predictor in the system, whatever predictor that is. To say, suppose ENSO has its own predictor, but ISMR has its own predictor. Like ENSO itself is a predictor, for example, but there may be more. But that relationship, first of all, that relationship between predictor and the predictant is actually nonlinear. So far, we have been and in the dynamical models takes that into account. However, because of the error growth problem, we cannot go beyond. But how do we? So if we can somehow find those nonlinear relationship separately from data and train the model, and what is the nonlinear relationship at one month lead, 2 month lead, or many n month lead, separately from a large volume of data, which is now available from model simulations. It's not necessarily from observation. Observation is limited, but we have a lot of model simulation. So using those model simulations, we can actually learn these relationships, and for each lead forecast, we can have a different model to predict it. And as a result, then you can go to a much longer lead time. And that is what has been demonstrated in the case of ENSO forecast. The AI models have been used to extend the forecast scale to a much longer time. And I think that kind of a thing is going to be feasible for Indian monsoon, or maybe other regional monsoon as well. And we have been actually working on slightly on that direction. So therefore, I think there is a way to use the available simulations and data that is available today. And obviously, recently you have seen that on weather prediction timescale also, this AI is using the same concept. They are training at different lead, the relationship between the driver and the predictable predictant, and then making those predictions and being successful in doing that as good as the NWP models or better. So the framework is there today. So I think we need to understand that and apply it properly. I think there is a possibility. I think this is the future that is going to happen. I'm sure in the operational forecast also, the AI is going to come in the next 10 years. I think already European Center, I hear that they have started looking at it with their forecast. So I think if we can get a better forecast, I think there is physical basis also. If you can train that properly, I think we can make a useful forecast, and those forecasts will be physically based. So it is not entirely data. It is not blindly we are doing it. We are training them for it on physically based processes, and then that gives us the desired result. So I think there is a conceptual framework is now emerging that AI could be used for from weather prediction as well as seasonal prediction. Seasonal prediction we have not gone. Very little has been done, but weather prediction already started. The effect. I think there are several papers have just come out recently.
Perhaps somebody in the attendees today is working on this. We're quickly running out of time, but I would like to ask if any Tim or Jill would like to have anything else I would like to add on to this about AI machine learning. I see Jill. It's okay, Tim. Yes.
No, yeah. Sorry, Jim.
I was only going to say that it's worth engaging with it. That's all. That I think that the model, the physical dynamical models, and the AI community need to talk to each other.
Right. Absolutely.
Yeah. And I know the Bureau are going down that track, or they're exploring their options at the moment in terms of machine learning, at least on seasonal forecasts. So.
We will never be able to do without the dynamical model. Dynamical models needs to give us more data, and the dynamical models are becoming better. So as a result, we are getting more and more large simulation, longer simulation. That data requires the spectrum of variability that is possible to train the models. So that so even with the existing models, we believe that because of their biases and all that, it gives you a variety of possibilities, which is good to train. So I think the model output is the critical part in terms of going forward with modeling. So therefore, I think without we cannot do, both have to work. And even for weather forecast, I think the success has happened only when these two communities have come together, because the computer science community does not know how exactly to apply it to the weather prediction. And weather prediction people have to come and show them how you have to apply. Otherwise, it will not work. So this is important. And you know, unfortunately, it is not happening in India. I was hoping that India it should happen faster, but it's not happening.
Well, I mean, we're coming together today. So yes, with that, I'm sorry we've run out of time, but I think it's a very nice message to end on. We have to come together. So thanks everyone for staying around, and thanks everybody for your excellent questions in the Q&A. I'm sorry they're all were discussing so much, having so much fun. We weren't able to address them all, but afterwards our speakers and that will answer the questions, and we'll post it on the webpage. I think the webpage that this webinar was announced on, along with the video. So please look out for that. So yes, I'm gonna have to wrap up. Yep. Yes.
Thea, can somebody send me this list? Maybe I will try to. I
yes.
Forget. So sort of, if they send me in an email, what is the list of questions and answers? Maybe
definitely we will send you. Don't worry, we do not. There's so many questions you don't have to remember them all. No worries. But yes. So before we bring the second Monsoon webinar to a close, I would again like to give a big thank you to our two distinguished speakers for their excellent presentations, and then all the panels, including my co-chair, for really that insightful discussion we had at the end. Thank you also to the International Monsoons Project Office and WMO, particularly Ushan, Hindumati, and Rajagopal, for helping organize this fantastic webinar. Also to the members of the Monsoon panel and the Regional Working Group on Asian Australian Monsoons for their inputs and putting this all together. And then finally, to all of you attending today, thank you so much for joining and participating. As mentioned at the top of this webinar, one of the aims of the Regional Working Group for Asian Australian Monsoons is to promote and facilitate active engagement and interaction with researchers, operations, stakeholders in all the different regional monsoon components of the Asian Australian monsoon. So I encourage us all to keep interacting after this webinar. We heard we even need to include more people in this community as we work towards addressing those outstanding questions about predicting and projecting monsoons. Okay, Jill, anything to add? Any from our anything to add? Anything from WMO?
Thank you very much, Thea.
If not, okay, thanks, and look out for the next webinar. Thanks, everybody.
Thank you. Okay, thank you. Thank you, Jill.
Thank you.